Okay, so today we're going to talk about combining functions. The different operations that you can use with functions would be adding, subtracting, multiplying, or dividing them. So our first one here, we have f of x, which is going to be our first function, x squared plus 2x minus 5, and then g of x, which is going to be negative 5x plus 14. And so we're going to try to combine them to create new functions. They might have different powers, or keep the same power as one of the parent function or the original functions here. And so this first notation here we're going to try to do is to add the two functions. So we would either use the notation f of x plus g of x, or we might see this as f plus g of x. So both of these mean the same thing, they need to add. So we're going to add these functions when we see this notation, either adding f of x plus g of x or f plus g of x. So this means that we're going to combine those two. So we're going to take x squared plus 2x minus 5 and add it to negative 5x plus 14. And I like to write the second equation with parentheses so I know what I'm doing there. And so now all that's left to do is we're going to combine like terms. So I don't have any other x squared, so I just have one x squared term. So that's going to hang out by itself. Then I'm going to add my 2x and my negative 5x. So I have 2 minus 5 gives me a negative 3x. And then I'm going to add my negative 5 and my positive 14 to give me positive 9. And this is the notation of f of x plus g of x. So all I've done here is I've added the two equations together. The last thing we want to do is try to figure out what the domain of our new function is. You can tell that by your parent function. In this case, our highest power here is a squared, which means this is a quadratic. And we know that all quadratics have the same domain, which is negative infinity to positive infinity. You could graph this on your graphing calculator and double check to see, but we know that the quadratic has that U-shaped graph so that it is going forever in both directions on the x-axis. We only care about domain for the combining function, so this is all we need to figure out here. The second thing that we're going to take a look at is subtracting functions. So when we want to subtract functions, we're going to take those same two original f and g functions here, except now we're going to subtract them. So when we want to subtract, we use the notation f of x minus g of x, or we can use the notation f minus g of x. Both of those mean the exact same thing. You might see either one of them. So you want to be familiar with both terms. So in this case, if we're going to subtract, we're going to set this up the exact same way. So we're going to write x squared plus 2x minus 5. And this time, we're going to be subtracting. So we're going to write subtracting negative 5x plus 14. So we've got both of our functions down here. But the difference is that this is a subtraction sign this time instead of addition. So when we subtract, we do have to distribute that negative sign to both terms in that second equation. And when we do that, we'll rewrite our equation as x squared plus 2x minus 5. Now, negative times a negative is a positive 5x. And a negative times a positive is a negative 14. Now when we combine like terms, we have still that first x squared term that doesn't have any other squareds. We'll take our 2x and our 5x and add them together to give us 7x. And negative 5 minus 14 gives us negative 19. Again, we'll take a look at what type of function this is. Now we have, again, a squared function or a quadratic. So we have that quadratic function. We know that all quadratics have a domain of negative infinity to positive infinity. So we're good. So we know that when we're subtracting functions, it's very similar to adding. We just have to make sure that we distribute that negative sign to both terms. Now the next operation we're going to look at is multiplying. We're going to use those same two equations again. So we use those equations. This time we're going to multiply. So the notation for multiplication looks a little bit different. So we're going to multiply. Then we want to take, we actually will see fg just like written together of x, or you'll see an f of x times g of x. And when we do this, all we're doing here is we're multiplying these two equations together, so we're going to actually use the box method. So in this case, I'm going to set this up with my box. So I have my x squared term, my positive 2x, my negative 5, and a negative 5x, and a positive 14. And so to do the box method, we're going to multiply each of these terms to find the ones in the middle. So negative 5x times positive x squared is negative 5x cubed. We get negative 10x, positive 25x. Just kidding, this is x squared, because x times x is x squared. 14x squared, then 28x, and negative 50, negative 70. And then when we combine like terms, these diagonals will actually be able to be added together as their like terms. So we get negative 5x cubed. 14 minus 10 will give us positive 4x squared. 28 plus 25 will give us 53x, and the negative 70 will go on at the end. Now we look at our new combined function here, and we have a cubic this time. But thankfully, cubics, again, have that same shape no matter what, even if it's a little higher, lower, expanded to the right or left. Our domain is always going to be negative infinity to positive infinity for a cubic. Cubics look like this, and that can continue to expand in both directions, to the right and to the left. The last type of function we're going to try to combine today is when we're dividing functions. We're actually going to use two different functions just for the purposes of an example. And when we divide them, a lot of times we don't see a lot of change to our equation, like we saw a brand new equation formed for our previous example. So when we want to divide functions, we'll see the notation that looks either like f of x divided by g of x, or we might see the notation that looks like f over g of x. Both of those mean the same thing. They mean to divide. So you may see either one of those. Just be familiar with those. Now in this type equation, we're going to actually change which equations we're using. So we're going to use the square root of x plus 5 as our f equation, and x squared minus 9 as our g equation. And so all we want to do here is actually write the one equation over the other. When we have f of x over g of x, all we're really doing is taking that top equation, the square root of x plus 5, over x squared minus 9. Now, this may look a little scary. There's nothing here we can actually simplify. So we're just going to leave it as is, and we type this in our calculator to see what type of function we're going to get. Now, hopefully, you're starting to become familiar with parent functions and understand that when we see x's in the numerator and denominator, this will end up being a rational function. So when you graph this on your calculator, I'm not going to, but you can, make sure that you throw parentheses around the numerator, then a division sign, and parentheses around that denominator. If you were to graph this, you should see something similar to this. If I can draw these in, you may or may not be able to see the asymptotes on your calculator, and I believe that it will look something like this. Probably not as beautiful as this drawing would show up on your calculator, but you will see that you have an asymptote at -3 and one at +3. Those are the two numbers that. Okay, so the denominator would be equal to 0. The two numbers that make the denominator equal to 0 would be +3 and -3, and we can't have a value there because then we'd be dividing by 0 here. So what happens is we have asymptotes at -3 and +3, so we're going to skip those values on the domain. So our domain of our rational function follows like the parent function, where you have a union for every asymptote that you have here. So we see that our graph goes from -infinity to -3, so -infinity to -3, and then we'll pick up in the other side of -3, so union -3 to +3, because that's where our next asymptote is, union 3 to infinity. So we have two asymptotes, therefore we have two unions on here. And so that's our domain for rational functions. So again, this is that rational function. So it's not a cubic, not a quadratic, where we know that the domain is negative infinity, positive infinity. But in this case, we have something that actually has some pieces missing from the domain, where we have those asymptotes at -3 and at +3.